AC generators are by far the most important devices used to produce electrical power today. Basically, all generators convert mechanical power into electrical power. AC generators produce AC power that's then used to fill most of our power needs. AC generators come in all sizes. They have a variety of applications in power plants and industrial settings. Now, the maintenance and construction of smaller AC generators are similar in many ways to motors. For that reason, we won't go into small AC generators here. Maintenance of that kind of equipment will be covered at another time in your training. What we will discuss is larger AC generators, those AC generators that produce a lot of power. In this program, we're going to discuss how AC generators work, how they're put together, and how you can keep them in good working order. Maintaining AC generators is usually an important responsibility of a maintenance electrician. Understanding how these generators work will enable you to perform this maintenance correctly. It's important, too, for any electrician to understand how AC generators work. This understanding is basic to an understanding of alternating current. With that in mind, we'll begin this program with a review of the basic principles of AC generator operation. Then we'll take a look at some of the parts of a typical AC generator and see how these generators are electrically connected. Also, we'll discuss the principles of voltage control, and we'll examine some auxiliary systems used with large AC generators. Finally, we'll see demonstrations of typical maintenance procedures that are often part of a maintenance electrician's job. So, let's begin with the principles of AC generator operation. As you probably know, all generators use induction to create an output voltage. When a generator is connected to a circuit, this induced voltage causes current to flow through the circuit. For voltage to be induced in a conductor, three requirements must be met. They are a magnetic field, a conductor, and relative motion between the field and the conductor. Let's look at how induction is involved in an AC generator's operation. Here's a simplified version of an AC generator. Its important parts are a rotor, here, and a stator, shown here. In this example, the rotor's an electromagnet that's connected to a DC power source. The stator's represented by a coil of wire wound on a steel core. Generators in your plant may have many coils of wire, but we'll show only one coil here. Let's energize the electromagnet. Direct current now flows through the rotor, creating a magnetic field around it, the first of our three requirements for induction. As in any magnet, there's a north pole and a south pole. We'll use green to show the north pole of the magnet and yellow to show the south pole. The coil around the core is a conductor, which is the second requirement for induction. The third requirement for induction, relative motion, occurs when we rotate the electromagnet. We can see how this simplified generator produces an AC output voltage. We'll use this graph to indicate the output voltage of our simplified generator. When the rotor's in this position, its magnetic field doesn't cut across the conductor, so there's no voltage induced in the stator coil. Now, as the rotor turns through 1/4 of a complete revolution, the rotor's north pole sweeps across the coil. Induced voltage in the conductor becomes maximum. As another quarter turn takes place, the induced voltage decreases until, again, there's no induced voltage in the stator coil. During the next quarter turn, the rotor's south pole sweeps across the coil. Maximum voltage is induced in the coil. But now its polarity is reversed because the coil's under the influence of a south pole. As we turn the rotor, the cycle repeats. The result? An alternating output voltage from the generator. We're now producing single-phase AC. You'll probably recognize that the graph of the voltage being produced by our simplified generator represents an AC sine wave. In AC generators, we use the term field to refer to the part of the generator that has DC applied to it to create a magnetic field. In our example, the field rotates. So this type of generator is called a rotating field generator. Now, in some smaller AC generators, the field doesn't rotate. These generators are called stationary field generators. DC is fed to the stator, and we take the output voltage from the rotor through slip rings and brushes. The slip rings are metal rings that turn with the rotor. The brushes are stationary parts that make electrical contact with the slip rings. But there's a problem with those slip rings and brushes. Most of the time, the current produced by an AC generator is a lot greater than the current used to create the generator's magnetic field. It's easier and more practical to build brushes and slip rings to carry low current than to carry high current. In the example we looked at earlier, the field rotated, and the output voltage was taken directly from the stator. The brushes and slip rings didn't have to carry high current. That's why AC generators are usually built with a rotating field. Earlier, we saw how to generate single-phase AC in a simplified rotating field generator. However, most AC generators are built to produce three-phase alternating current. They're built that way because three-phase AC is more efficient than single-phase AC. Now, to get from single-phase to three-phase AC, we'll need to modify our simplified generator just a bit. The modification? More coils in the stator. The three coils shown here are spaced 120 degrees apart around the stator. Let's see what happens now when the rotor turns. Each coil now has a separate AC voltage induced in it. However, maximum voltage occurs at different times in each of the three stator coils. In the first phase, maximum voltage occurs as one pole of the field passes the first phase coil. Maximum voltage in the second phase occurs as the pole passes the second phase coil. But the first phase voltage has already decreased and reversed polarity. In the third phase, maximum voltage occurs as the pole passes the third phase coil, while voltage continues to change in the other two coils. Here's what the three output voltages look like on a single graph. We're now producing three-phase AC. You'll find that most AC generators produce three-phase AC. Let's stop right here. In this segment, we've covered the basic principles of AC generator operation. We've listed three requirements for induction and shown how a simplified generator uses induction to generate single-phase or three-phase AC. Before we continue, take the time now to review this segment in your text. Ask your instructor to clear up any points you're not sure of before we go on. Now that we've discussed the basic principles of AC generator operation, we're ready to talk about some of the different ways AC generators are built. First, we'll discuss the factors that determine a generator's speed of rotation. We'll also take a look at some of the major parts of an AC generator. We'll finish this segment by covering two different ways that an AC generator can be connected to its electrical load. Okay. First, let's cover the factors that determine a generator's speed of rotation. This speed of rotation is determined by the required AC frequency and the number of magnetic poles in an AC generator's field. It's usually necessary for generators to turn at a constant speed, so they'll produce a constant frequency. For example, in the United States, generators usually produce a frequency of 60 hertz. This means the current alternates through 60 full cycles every second. Let's take a look at how rotational speed determines frequency. Here's our simplified AC generator. As we saw earlier, it produces one AC cycle for every complete revolution of its rotor. Now, to produce 60 hertz AC, our generator would have to revolve 60 times per second, or 3,600 revolutions per minute. Of course, our rotor would have to turn faster to produce a higher frequency, slower to produce a lower frequency. The second factor that determines rotational speed is the number of poles in the field. If our generator had more than 2 poles, it would be able to turn slower and still produce a 60 hertz frequency. Let's see why. Here's a 2-pole, single-phase AC generator. We'll turn the rotor through one complete revolution. We saw in the last segment that this produces one cycle of alternating current. Now here's a 4-pole generator. As you can see, its rotor has 2 north poles and 2 south poles. As we turn the rotor, we only need to turn it half as far to produce one cycle of alternating current. That's because 2 rotor poles pass the coil in 1/2 of a revolution. So in a 4-pole generator, we only need to turn the rotor half as fast to achieve the same frequency as a 2-pole generator. Okay, we've seen that rotors in generators can have different numbers of poles. Now let's take a look at a couple of different types of rotors: salient pole rotors and high-speed or cylindrical rotors. A salient pole rotor has windings which are wrapped around metal pole pieces. A shaft supports the rotor assembly. Salient pole rotors are usually found in relatively low-speed AC generators. Their windings would be torn loose if they were used in higher speed situations. This is because of centrifugal force and other stresses that occur at high speeds. When AC generators are required to operate at high speeds, you'll usually find cylindrical rotors. Here you see the core of a cylindrical rotor. It has slots machined into it. The windings are secured in these slots. Centrifugal force and other stresses affect a cylindrical rotor less than they affect a salient pole rotor. Here's a picture of a cylindrical rotor. They're often pretty big and need to be removed by cranes when they're worked on. Now, the windings in a rotor have direct current flow through them that comes from an outside source. DC passes through the rotor's windings to create the rotor's field. The source of that DC is called an exciter. Here's an example of an exciter that's driven off the same shaft as the rotor of an AC generator. Some exciters are DC generators. As you probably know, DC generators have commutators and brushes that enable them to produce a DC output. When a DC generator is used as an exciter, a second set of brushes is required to get DC power to the AC generator's rotor. These brushes make sliding contact with slip rings that are connected to the rotor windings. Another fairly common type of exciter is called a brushless exciter. This is an AC generator that's driven by the same shaft as the main generator. A brushless exciter has diodes that rotate with the rotor and convert AC to DC. We'll talk more about exciters in the next segment. Let's go on now and cover the other major generator part, the stator. Stators can be built a number of different ways, but they all have certain common features. Stator windings, a stator core, which concentrates and directs the magnetic field within the stator, a stator frame, which contains and supports the core and windings, and end bells, which close the end of the generator's frame. So, we've seen two basic generator parts, the rotor and the stator. Remember, most AC generators are rotating field generators, so their output voltage is taken from the stator. We're going to talk now about how the coils in a typical three-phase stator are connected. Three-phase AC generators are usually connected in one of two ways, delta or Y. In a delta connection, the three-phase windings are connected end to end. The output connections are made between the windings. But most AC generators aren't built this way. Why? Well, when a generator is delta connected, its output voltage for the same amount of power produced is lower than it would be if it were Y connected. In most situations, a high output voltage is desirable. Therefore, a Y connection is used in most AC generators. As you can see, one end of each winding is connected to a common point. With this arrangement, voltage is higher for a given power level than in a delta-connected generator. An important feature of Y-connected AC generators is that they can be connected to ground conveniently. As a safety measure, their common point of connection, or neutral point, is connected to ground. This helps to detect grounds elsewhere in the generator. Normally, there's no current flow through the neutral point to ground because there's no complete circuit. But if another ground occurred, there would be current flow through the neutral and through ground. That current flow could then be an indication of a serious generator problem. Larger AC generators use a neutral transformer to both detect and limit current flow through ground. Here's how it works. This is the primary side of the transformer, and this is the secondary side. The primary side's built so that it has high inductive reactance. High inductive reactance in the primary side limits current flow if a ground occurs. Normally, there's no current flow through either side of the transformer. If a ground occurred, a limited amount of current would then flow through the primary side of the transformer. This would induce a voltage in the secondary side of the transformer. The secondary side of the transformer is connected to instrumentation that detects current flow through the transformer. This instrumentation either initiates an alarm or indicates in some other way that there is current flow through the transformer. In some cases, it'll shut the generator down. Okay, let's review what we've covered. We've seen two factors that affect the speed of rotation in an AC generator. In addition, we took a more detailed look at two basic generator parts, the rotor and the stator. Finally, we talked about delta and Y connections and learned the purpose of neutral transformers. That's a good bit of information to deal with. So now's the time to go back and read segment 2 in your text. Make sure you have a good understanding of this material before we continue. The next thing we're going to look at is how we control an AC generator's output voltage. Now, this is a pretty complex subject, and it's not going to be possible to cover all types of control systems. What we'll do is cover the basic principles involved in voltage control, so you'll better understand the control system in your plant. Voltage control is important because a generator's output voltage varies with changes in load. In most situations, the load on a generator is constantly changing. Take, for instance, a large AC generator that's used in a system to provide power to a city. Power requirements vary considerably at different times of the day. That changes the load on the generator. Most electrical equipment needs a fairly constant voltage in order to function properly, so voltage must be controlled to keep it from changing every time load changes. Let's see how voltage is controlled. We'll start with the factors that determine an AC generator's output voltage. They are the speed of rotation, the design of the generator, and the strength of the field. The first factor is the speed of rotation. Now, when an AC generator turns faster, more voltage is induced. This increases the generator's output voltage. So we could control output voltage by controlling the generator's speed. However, this usually isn't done because speed also affects frequency. Most AC generators have to operate at one frequency, so their speed can't change. The second factor is the design of the generator. A generator's output voltage is determined by the way it's built. The physical arrangement of the conductors inside the stator and the number of conductors are both important design considerations. But these considerations are determined prior to the manufacture of the generator, so a generator's design can't be used to control its output voltage. That leaves us with a third factor, the strength of the field. Now, the field's created by direct current flow through the rotor windings, so we can vary the field strength by controlling current flow through the windings. Increasing current flow through the field windings increases a generator's output voltage. Current flow that creates an AC generator's field is called excitation. Excitation can come from any DC source, but it's usually provided by another generator called an exciter. Excitation systems provide a way to control an AC generator's output voltage. Let's examine a typical voltage control system. The system used to control the voltage of the AC generators in your plant may not be like that of the one we'll be talking about, but the principles involved will be the same. In our typical system, we'll use a self-excited DC shunt generator as our exciter. Let's briefly review how it works. Its armature is here, its shunt field here, and it has a field control rheostat here. Initially, there's a small residual field in the DC generator. When its armature turns, induction produces a voltage, and current flows through the shunt field. The generator's magnetic field increases, causing more induced voltage and more current flow through the shunt field. As the process repeats, voltage builds to a value that's determined by the resistance of the shunt field and the rheostat. Here's the AC generator, its field, its slip rings and brushes, and two leads that connect it to the exciter. Here's the stator, and its three leads. If we rotate the exciter, direct current flows through the AC generator's field. The direct current is the excitation for the AC generator. Now, here's where voltage control comes in. You recall that there's a field control rheostat in the exciter. We can increase or decrease the AC generator's output voltage by moving this rheostat. When we move the rheostat in this direction, the total resistance in the shunt circuit increases. The output voltage of the exciter is determined by the resistance of the shunt field and the rheostat. When that resistance increases, current flow through the shunt field decreases. That decreases the exciter's output voltage and current flow through the AC generator's field. So the AC generator's output voltage decreases. The exciter field control rheostat gives us manual control of our AC generator's output voltage. One additional step will make our system automatic. What we need now is a way to sense the AC generator's output voltage and adjust the exciter field to keep voltage constant at all times. To do that, we'll use a transformer, a solenoid, and a spring. The transformer steps down the AC generator's output voltage to a level the rest of the system can handle. Here's the solenoid. It's a coil of wire containing a movable metal core. When current flows through the coil, it produces a magnetic field, which attracts the core. The core, in turn, is connected to the exciter field control rheostat we saw earlier. Now the solenoid will only move the rheostat in one direction, but we need to be able to adjust the rheostat in either direction. The spring lets us do that. Let's see how our voltage control system responds to an increase in the AC generator's electrical load. When load increases, the AC generator's output voltage decreases. Our solenoid senses the decrease in the AC generator's output voltage. In the coil, there's now less current flow, so its magnetic field decreases. That allows the spring to pull the core out of the coil, and the rheostat moves accordingly. When the rheostat moves like that, it decreases the resistance of the shunt circuit. Decreased resistance means increased current flow in the shunt field, and an increased exciter output voltage. You know the rest. As the exciter's output voltage increases, current flow through the AC generator's field increases, and the AC generator's output voltage increases. Our system will work the other way too. If the AC generator's output voltage increases, the system will act to decrease the excitation going to the AC generator's field. We now have an example of a system for automatic AC generator voltage control. We've seen that the control system will act to either raise or lower exciter output voltage to maintain a constant AC generator output voltage. This voltage control system illustrates the basic elements that any system must have to control an AC generator's output voltage. Those elements are a sensing unit, a control unit, a reference, and a source of DC power. In our example, the solenoid was the sensing unit. The rheostat was the control unit. The spring provided a reference, and the exciter was the source of DC power. Different voltage control systems use different components to perform these functions. In most cases, the control systems are much more complicated than the one we've just talked about. But even the complicated ones have the same basic elements that we've discussed in this segment. Now is the time to go back and read the section on voltage control in your text. If you have any questions, have your instructor answer them at this time. Generators come in all sizes, from the smaller ones used in your car to larger ones used in power plants. All produce power, and with that power, heat. In smaller AC generators, the heat's removed by airflow, but in large AC generators, a lot of heat's produced, and special systems are needed to remove it. Now, as a maintenance electrician, you'll need to know how some of these systems function so that you can work on them. In this segment, we'll see how some typical heat-removing auxiliary systems work. We'll look at a hydrogen cooling system and at a seal oil system associated with it. Then we'll see a water cooling system. First, the hydrogen cooling system. Large AC generators often use hydrogen for cooling. We'll see why they use hydrogen in just a second. But for now, let's take a look at a simplified hydrogen cooling system and see how most of them operate. The generator's filled with hydrogen, which circulates around the inside. Hydrogen circulates through the rotor and stator windings, continually picking up heat produced by the generator. Then, the hydrogen flows through heat exchangers, where the heat's removed and then flows back to the windings. The hydrogen never leaves the generator. It follows a closed flow path. But the heat does leave the generator. Water flows through tubes in the heat exchangers. In the process, it picks up heat from the hydrogen and carries that heat out of the generator. The main reason that hydrogen rather than air is used to cool large AC generators is that hydrogen has a higher heat capacity than air. It can absorb more heat, so it can remove more heat from the generator. Also, hydrogen's better because it's less dense than air, and it causes less wind resistance. That makes it easier for the rotor to turn in the generator. But there's a problem with hydrogen. It's explosive when it's mixed with air. So it's necessary that no air be allowed to enter the generator. The generator's frame keeps air from mixing with the hydrogen inside it. However, there are two places where it's possible for air to enter. These two places, where the rotor's shaft passes through the generator's end bells. At these two places, special seals keep hydrogen and air from mixing. The seals are part of a hydrogen seal oil system. Here's a diagram of a simplified hydrogen seal oil system. The diagram shows the seal on one end of the generator, but the seal on the other end works the same way. There are two sides to each seal, the hydrogen side and the air side. Here's what a cross-section of the seal looks like close up. Oil's fed into the center of the seal. There are two ways in which oil can flow. In our example, the left side of the seal leads to the hydrogen side, and the right side leads to the air side. Oil flows past seal rings and along the shaft in both directions. Oil flow to the hydrogen side keeps hydrogen from entering the seal, and oil flow to the air side keeps air from entering the seal. This prevents air and hydrogen from mixing. Let's start on the air side and follow oil flow through the system. Oil flows from the seal to a tank called an air detraining tank. We've got to get air out of the oil before we can use it again in the system. If air is left in the oil, it could mix with hydrogen when oil is pumped back into the seal. What the air detraining tank does is to allow oil to stand for a period of time so that air bubbles out. Then, oil flows into a vacuum tank, which removes any remaining air or moisture. A vacuum pump maintains the vacuum in the tank. Oil flow from the hydrogen side of the system ends up eventually in the same vacuum tank. Let's return to the seal. Now, we'll follow the oil flow through the hydrogen side of the system. After the oil flows out of the hydrogen side of the seal, it goes into a hydrogen detraining tank. The oil picked up a small amount of hydrogen gas when it was in the generator, so we need to get that hydrogen out to avoid the possibility of hydrogen mixing with air. The hydrogen detraining tank works like the air detraining tank, only now hydrogen is bubbled off. After leaving the tank, oil enters the vacuum tank, where we left off before. The oil is ready now to be circulated by the seal oil pump. Oil is forced back into the seal, and the process repeats. So, that's how the hydrogen seal oil system works. Now, let's move on to the third auxiliary system that's sometimes used in large AC generators. This system cools the generator by forcing water through the generator's stator windings. The stator windings in a large AC generator are made of bars. Now, this is a piece of bar from a generator's winding. Around the outside of this bar is an insulating material. In the center, a conductor. Now, as you can see, the conductor has small holes built right into it. When the stator cooling system operates, water flows through the holes and carries heat away from the generator. The water used in the cooling system has to be extremely pure, because impurities would make the water a conductor. So, the water is specially treated before it's put into the system. Here's a schematic of a typical water cooling system. If the AC generators in your plant have a water cooling system, they're likely to be built similarly to the one we'll describe here. Let's follow water flow through the system, starting at this pump. The pump forces water through coolers and then into the generator, where it flows through the windings. As it does that, it picks up heat and carries heat out of the generator. From the generator, the water flows into a storage tank. The pump draws water from the storage tank and circulates the water back through the system again. Well, that just about covers the water cooling system. We also took a look at a typical hydrogen cooling system and saw how a typical hydrogen seal oil system works. Although the systems in your plant may not be exactly like the ones we've described, they'll probably work much the same way. At this time, read through the section on generator auxiliary systems in your text. When we come back, we'll see some examples of maintenance procedures that are commonly performed on typical AC generators. So far in this program, we've talked about how AC generators work and about some of the auxiliary systems that are used with large AC generators. For the remainder of this program, we'll concentrate on some of the maintenance procedures that are typically performed on AC generators. The first procedure we'll cover is brush maintenance. Now, not all AC generators have brushes, but on the ones that do, they require frequent attention. For instance, on the generator in our example, brushes are checked every few days. Let's take a look at this particular generator and see where its brushes are located. This generator is built a little differently than the generators we've talked about so far. Its exciter is a shaft-driven DC generator. A set of brushes collects the exciter's output from its commutator. Then the output goes from these brushes to a second set of brushes that ride against slip rings. These slip rings are attached to the windings of the AC generator's rotating field. Current flow from the exciter through the field windings creates the AC generator's magnetic field. In this case, the exciter is a separately excited DC generator. To operate, it must have a separate source of DC power. This comes from another DC generator called a pilot exciter. The pilot exciter is a small, self-excited DC generator, and its output is collected by a third set of brushes. The pilot exciter supplies excitation for the main exciter. So we've actually got three generators here: the pilot exciter, the main exciter, and the AC generator. All three are driven by the same shaft. Now, this is a fairly common type of setup for an AC generator's excitation system. Another arrangement that's commonly used is a main exciter and pilot exciter driven by a separate electric motor. Here's what that arrangement looks like. With either of these exciter arrangements, the brushes must be checked regularly. This can be done with the system in operation or with it shut down. From a safety standpoint, it's better to do brush maintenance with the equipment shut down, but that isn't always practical. In many cases, it's necessary to keep the equipment in continuous operation. In that case, brush maintenance is routinely performed with the equipment online. Now, this is a job that can be extremely dangerous if you don't know exactly what you're doing. In a minute, we're going to see a demonstration of how this job can be done safely and effectively. The electricians are thoroughly familiar with the equipment they're working on, and they're aware of the hazards involved in the job. Now, before you attempt any of this work, you'll need to be very familiar with the AC generators in your plant and with any special precautions that your plant requires. In general, there are two major hazards. First, there's the danger of electrical shock that always exists when working on energized equipment. Second, there's the danger of working close to rotating equipment. Both of these hazards can be avoided if you're careful. Okay, usually the first step in the brush maintenance procedure is to check all the brushes. The electrician starts by checking each of the pilot exciter brushes to make sure they're making contact with the commutator. He does this by pressing down on the top of each brush. Now, by doing this, he verifies that the brushes are not hung up in their holders. Next, he looks at each of the brushes and their brush rigging. He's double-checking for problems he might not have seen earlier. He's looking for problems like sparking and arcing at the brushes, loose wires or parts, and brushes that are too short. Any short brushes will have to be replaced. If he finds other problems, he'll report them to his supervisor. Next, he inspects the main exciter brushes in a similar manner. Again, he looks for good contact between the brushes and the commutator and for anything unusual. There are more brushes on the main exciter than on the pilot exciter, but the inspection procedure is basically the same. Here, the electricians found a problem, a short brush. It would wear out before the next time he checked it, so he'll replace that brush later, after checking the other brushes. He's got to be very careful not to touch a positive and a negative brush at the same time. If he did, current would flow from the negative brush to the positive brush through his body. To avoid this, he works with only one hand while he inspects the brushes. Also, he's careful not to touch the rotating shaft. After the electrician finishes checking the rest of the main exciter brushes, he moves on to check the brushes on the generator's slip rings. He follows the same basic inspection procedure. He carefully checks each brush for contact with the slip ring and keeps an eye out for anything unusual. Well, it looks like there's only one brush that needs replacing on this side of the generator. The electrician has to check the brushes on the other side of the generator as well. Then, he'll go and get as many replacement brushes as he needs. To replace the short brush, he's going to have to work with both hands in the generator. He'll need someone there to hand him the replacement brush when he's ready to put it in. Also, because of the hazards involved, it's a good idea to have someone there to help. To replace a brush, the first step is to disconnect the brush's pigtail, the wire that's attached to the brush. The electrician coils up the wire so it won't accidentally come in contact with anything else. Then, with his other hand, he lifts the tensioning device off the brush and pulls the brush out of its holder. He hands the old brush to the other electrician, who then hands him the new brush. The electrician slides the new brush into the brush holder and replaces the tensioning device. Then, he carefully reconnects the brush's pigtail and straightens it out so it hangs straight. That takes care of the brush. Next, the electrician cleans the commutator to remove carbon dust that's accumulated there. As the brushes wear down, carbon dust is produced. Now, carbon is a conductor, and if carbon dust builds up, it will eventually short the commutator segments together. Carbon dust could also cause grounds. He uses a canvas wiper because canvas is sturdy enough to be held against the commutator without tearing. He's very careful to control the movement of the wiper so that it doesn't get pulled up against the brush rigging. After he's finished wiping the exciter commutator, he moves on to the pilot exciter, while the other electrician closes up the main exciter. Again, he holds the canvas wiper against the commutator to remove carbon dust from the commutator. Once the pilot exciter has been cleaned up, the job's finished. Well, the procedure you've just seen is typical of the type of maintenance that's routinely performed on generator brushes. But don't forget that the generators in your plant are probably not built exactly like the one that was used here. In order to safely perform this maintenance, you'll need to be very familiar with the way the generators in your plant are built and with your plant's procedures. For right now, though, take a few minutes to review this material in your text. Make sure you understand in general how this work is done. If you have any questions, clear them up with your instructor. Most manufacturers of large AC generators recommend that both the generator and its prime mover, usually a steam turbine, be disassembled and inspected every 3 to 5 years. So overhauling isn't done very often, but it is a job that you're likely to be involved with from time to time. So that you'll better understand how a generator is taken apart and inspected, we'll go through a description of an overhaul of a typical large AC generator. We'll concentrate on the major steps that must be performed during the overhaul. After the generator's been shut down, the first major step will usually be to remove the hydrogen. The generator can't be opened up with the hydrogen still in it. This would allow hydrogen to mix with air, an explosive mixture. The hydrogen's removed by forcing it out with an inert gas. like carbon dioxide. When carbon dioxide is used, it's forced into a distribution pipe at the bottom of the generator. Since it's heavier than hydrogen, carbon dioxide fills the generator from the bottom, pushing the hydrogen out the top through a vent. The vent piping then carries the hydrogen out of the plant where it can be safely released into the atmosphere. Then the carbon dioxide is removed from the generator by forcing air into it. When all the carbon dioxide's out of the generator, it's safe to begin opening the generator up. We'll use a cross-section drawing of a typical generator to show how the disassembly is done. Keep in mind, though, that what we'll be talking about is the procedures involved in a typical disassembly. These procedures may not be exactly like the procedures used in your plant. To begin, the generator must be uncoupled from its prime mover and its shaft-driven exciter, if it has one. A crane lifts the exciter out of the way. The end bells of a large generator usually come in two separate pieces, an upper half and a lower half. Now the next step is to unbolt and remove the upper half of both end bells. The lower halves won't be removed until later on. Next, the bearings are removed. The bearings also come in two halves. The top halves can be removed simply by unbolting them and lifting them off. But the rotor rests on the lower halves, so the rotor will have to be supported before the lower halves of the bearings can be removed. One way to support the rotor is to use a jacking device mounted on the lower half of each end bell. The device jacks the rotor up slightly so it no longer rests on the bearings. Then, the lower half of each bearing can be rolled out from under the rotor shaft. The next step in disassembling the generator is to remove the rotor. Because the rotor is so heavy, and because of the way the generator is built, this is a fairly complicated procedure. There are 2 points to keep in mind during this procedure. First, the rotor must be adequately supported at all times. Second, if the rotor hits the inside of the stator, both the rotor and the stator could be damaged. The exciter end of the rotor is supported with a sling that's attached to the end of the stator's frame. Then the lower half of the end bell can be lowered. This gives the rotor enough room to slide out of the stator. Next, a lubricated steel plate is placed in the gap between the rotor and the stator. A slider goes between the rotor and the steel plate. The slider, or field shoe, will slide along the steel plate as the rotor is pulled out. The rotor is lowered onto the field shoe so that it supports that end of the rotor. Then the lower half of the second end bell is lowered out of the way. Now the exciter end of the rotor can be supported by an overhead crane. The rotor is pulled about halfway out, sliding on the field shoe. This must be done very carefully so that the rotor doesn't touch the stator. When the rotor is a little more than halfway out, it's blocked in place. Now the crane shifted to the center of the rotor. In that position, the crane will support the entire weight of the rotor. Now the blocking in the field shoe can be removed. The crane then moves the rotor the rest of the way out. The generator is ready to be inspected at this time. Inspection is usually done by an expert who's thoroughly familiar with the way the generator is built and who's aware of things that are likely to go wrong with it. Basically, this inspection is intended to detect 2 types of problems: mechanical damage, such as loose or broken parts, and damage to the generator's insulation, such as burns or breaks. There are also a number of tests that are usually performed on a large generator during an overhaul. The tests performed on a particular generator depend on its construction, the manufacturer's recommendations, and its past operating history. But there are 2 types of tests that are routinely performed on almost any large generator. These are magometer tests and high potential tests. These tests can be done prior to disassembly, and in some cases are done to determine whether the generator should be disassembled at all. The basic test procedures are pretty much the same, whether the generator is assembled or disassembled. Let's take a look at a typical magometer test. We used a megometer to measure insulation resistance. The megometer indicates resistance in millions of ohms. Megometer readings are usually taken during overhaul in order to evaluate the condition of the generator's insulation. This diagram shows how the megometer is connected to the generator windings. Before attaching the megometer, make doubly sure that the generator is electrically isolated from all associated equipment. Then, the 3 output terminals are tied together, and the line lead from the megometer is connected to them. The other lead from the megometer is connected to ground. With this test setup, the megometer will measure the resistance through the generator's insulation to ground. The megometer is usually operated for 10 minutes. During that time, 2 readings are taken, one at the end of 1 minute and the other at the end of 10 minutes. The ratio between these 2 readings is called the polarization index. Both the readings and the polarization index provide an indication of the condition of the generator's insulation. A high potential test is also a test of the generator's insulation. In a high potential test, or high pot test, a high voltage is applied across the generator's insulation. This is usually a voltage greater than the generator's normal operating voltage. A high pot test determines if the generator's insulation will withstand the test voltage. The high pot test setup is very similar to the megometer setup. First, the generator is isolated electrically, and its output terminals are tied together. Then the high pot tester is connected to the terminals and used to apply the test voltage. Generally, the test voltage is maintained for 1 minute, but the length of time may vary. The length of the high pot test in your plant will be determined by plant or company policy. If the insulation withstands the test voltage, it passes the test. Following the test, the generator must be discharged to remove the test voltage. Well, that just about does it for our discussion of overhaul maintenance. We've covered some of the procedures that you're likely to be involved with if you take part in an overhaul of a large AC generator. For now, read through the overhaul maintenance section of your text. When you finish that, go back over any of the other sections of the text if you need to. Be sure you've cleared up any overall questions you may have about the operation or maintenance of AC generators. It'll be part of your job to see that things like this don't happen because of a faulty AC generator.